All right, let's take a look at a few more of these. This one here I thought is really important because it helps point out what a human has to do here. Like I said, the fundamental lesson here is the AIs are not as intelligent as you think they are. Humans have to add a lot of the intelligence. So here, for example, you're going to process some input data, and what you have is data from some government agency on housing prices in California in the 90s. So you've got zones that are sort of like counties, areas of the latitude, longitude, the age of the house, the total number of rooms, the population, and the house value. And what you're going to try to do is predict the house value from all these other numbers. That's the goal. And so if you use the head command in the database, you can see what the various categories are and so on. Um, and so you can get counts of them. And now it turns out one column is not numerical. All of them are numerical except for ocean proximity, which is alphabetical. And so if you look, it has only five possible values like this. So now you can do statistics for the numerical ones. You can have like mean, standard deviation, and all that jazz, and you can plot histograms of them, and you'll see that it doesn't fit simple models as you'd expect. In California, houses are not evenly distributed geographically. There's a huge center near San Francisco and near Los Angeles, and not much of anything else. So latitude and longitude are these two peaks. Now look at the housing median age, which also shows no simple pattern because, of course, there's things happened at a certain time. There was a boom in housing, then there's a crash in the economy, no housing, then another boom. And notice this here, a huge spike at 50. And this is part of, like I say, why you need humans and your AI can't do it. That's obviously false. Obviously, the data had some kind of limit, and the limit was 50. And you can't give anything more than 50 years or 51 years or whatever this is. So this giant spike in houses does not reflect the real age of houses. It's something like, if it's older than this, just put down 50. So your model better not try to fit that data, or you're not going to be fitting the actual population. You're going to be fitting the artifacts. And you see the same thing wrong with house value. Apparently 500,000 was the maximum possible house value. So everything above that is just rammed into this one bin. So this does not reflect the actual phenomenon you're trying to measure. It reflects an artifact of the data. And we're going to see a lot more of these. So you split the thing into training and test sets, and even that is harder than you'd think. So the first thing you'd do is take 80% of the data randomly and put it in the training set, and hold back 20% of the data to test your model. That might seem like the right things to do, but it is not the right thing to do because there is one ultra important parameter here, which we're going to see. And you have to understand biased sampling. Now, suppose you're measuring some property of human beings, like their height, that is strongly dependent on their sex. Women are shorter than men. If that's the case, if you have a sample, now 51% of the population are women. So if you just made a random sampling of from people, then you would find that the most likely thing is you'll have 51% of the sample women, but you have a reasonably high chance of getting 53 or 54% women in your sample. And if you do, it's going to be a biased sample that does not correctly reflect the underlying phenomenon. So to avoid that, you do stratified sampling. Instead of just choosing randomly 80% of the data, you break the data up into bins by income, 5 bins of income, and then you find the percentage of the data that's in each of those income categories, and then you choose that many percentage for your sampling. You carefully, that's called stratified sampling. You choose the sample to reflect the real population of the important variables in your background. So this is in your population. And so again, notice this is a human putting in stuff. And the obvious thing this applies to, which I thought about immediately, is voting. They tried to do a poll and determine like who's going to win the election. And this is what you have to do. You have like some thousands of people you called on the phone, and now you're going to try to adjust it. So the percentage of black people, the percentage of rich people, the percentage of people in cities, and so on matches what you expect. And this is a matter of human judgment. If you don't do this, you're going to be less accurate. But when you do this, you're putting in your bias, your assumptions. So it's tough. So anyway, you split the data. If you do it randomly and then stratified sampling, you'll get a better real representation of the population. And now you can look for more problems. So if you plot the data, longitude and latitude, and how many houses are there. You get this. Now, this is a very misleading graph because the dots pile on top of each other. You can't see how dense they are. So if you use transparent dots, you can see more clearly that these population centers near San Francisco and Los Angeles are very dense, and the rest of the state is a lot less dense. And you can include like population and housing value here and show, of course, the most expensive houses are on the coast in the San Francisco and LA area, and all the inland ones are much cheaper. All right, but then the real issue is correlations. And here's where you can determine how predictive each of these parameters is for housing price. And of course, house value is the actual number we're predicting, so that's 100% predictive. The question is, what other parameters will predict it? And a correlation coefficient, if it's 1, that means it's 100% matched. If it's 0, that means it gives you no information at all to predict the other one. Any other number deviating from 0, positive and negative, means it has some predictive power. And here you can see income has large predictive power, which makes sense. The rich people live in an area where the houses cost more. Rooms, the rest of these are all really weak, like the most 13% predictive, not very good. But here you meet another bizarre thing. Since you are measuring real world measurements and they are not really independent measures of anything, combining them can give you a new feature that's more predictive. But first, we're going to see more artifacts. So if you make correlations between parameters, here's house value against house value. That's just the population. So here's house value against income. And as you can see, very predictive. And the rest of these, not that much correlation. But if you take a close look at house value against median income, you're going to see problems. Here's the one I mentioned before. There seems to be a ceiling at 500,000 and a whole bunch of data there that shouldn't really be there. It should be up here somewhere. And then you see another echo at 450 and 350. There seems to be some data where they rounded off and shoved dots here that don't really belong here. So if you fit this data, you're not going to be fitting the real population. You should remove these data points or move them to the mean or something. And again, that's putting in like distortion and human bias in the data. Makes me very nervous. As long ago, I was a physical scientist measuring physical parameters, and you wouldn't do that. But in more complicated data sets, you have to do that to try to get closer to the real data. And then, like I mentioned, you can do attribute combinations. And when you do that, there's a combination that is very predictive called bedrooms ratio, which is the number of bedrooms divided by the total number of rooms. Neither one of those numbers alone is very predictive, but the combination of them is predictive. So this is another thing that's not obvious at all. The combining the data to make a new derived data column may actually get you a lot of predictive power because the errors will cancel out and the actual value will be retained. So that gives you a clue, all the human judgment that goes into this. And now you can do some tasks like classification. Here we're going to try and read these digits. These digits were written down by census takers in the US. And there's a large database available of these you can download with the right number. You can learn to recognize these numbers. And most of them are pretty easy, but some of them are a little harder to see. And notice you have not only handwriting mistakes, you have artifacts of the photograph here, like the edge of the photograph. But anyway, so now you break it into training and testing sets, 60,000 images to train on and 10,000 images to test it on. And then you can train various classifiers. Here, what we're going to do is just decide if the number is a 5 or not a 5. So we have a single binary choice. So you take the input image, you break it into separate pixels, 794 separate pixels, which, as I mentioned, I object to from a point of a vision scientist. That is not what you should do here. You should break it into features like this is a line, this is the background. That's what pre-processing you would do to get good results from a computer model of vision. But in this case, we're going to be stupid and just treat every pixel as an independent, unrelated measure. So we're going to destroy and lose the data that some pixels are near each other and some pixels are far from each other, and then go to a neuron. So you can make a binary classifier doing that. Again, we're just going to use stochastic gradient descent to improve this. It'll run for a series of epochs. Now, last time we did this, we did it for like 100 or 500 epochs, picking an arbitrary number. Here we're going to do what people really do. The way you find the bottom is you take a little step and it gets better, a little step and it gets better. You keep taking steps, and as soon as it gets worse, then you stop because you've apparently hit the bottom. So you can see here's the loss going down 78, 77, and now it went up. So we stop. That's one way to do it. It's not perfect, of course. You might be in a local minimum when there's a global minimum somewhere else, but in a simple case, this is the easiest way to know when you've hit the bottom. So here it is, doing predictions. The first image was a 5, so it's true that it's a 5. The next two images are a 0 and a 4, and it gives you false, saying that's not a 5. So the first three predictions are correct. And you can see here, or so now you ask, how do you measure the accuracy of a model? Well, you can do it by cross-validation. You split the training data into three groups, and then you do three models, training it on 2/3 of the data and testing it on 1/3, and then you just shuffle those thirds around. That's called that cross-validation. And so the three accuracy measures here were 95%, 96%, and 96%. So that sounds pretty good, but remember, the data had an even distribution of all 10 digits. And so if I just called them all not 5, I would get 90% right. So 96% is not as impressive as it might sound. And then you can more accurately measure it with the confusion matrix. This is the number of not 5s that were correctly determined to be not 5s, and this is the number of 5s that were correctly determined to be 5s. This is the number of not 5s that were incorrectly called 5s, and this is the number of 5s that were incorrectly called not 5s. So you can see the non-5s have a very small chance of being a 5, about 1% chance, 600 out of 50,000, but the 5s have almost a 30% chance of being called not 5. 3,500 were correct, but 1,900 were incorrect. So this is a more accurate representation of your performance of your model. It's more complicated than just a simple number, percentage right. You have different kinds of errors that are possible, and you can decide based on your situation which errors are more important to you. So there's a thing called precision, which is true positives over true positive plus false positives, and that's 83%. There's a thing called recall, which is true positives over true positive plus false negatives, and that's 65%. And then there's something called an F1 score, which combines them in a number that would be 100% if it was perfect, 73%. And then remember, the model doesn't actually tell you 5 or not 5. It gives you an analog output. And you can then decide what the threshold is going to be. You have a low to a high signal here. So low signals means it's not likely to be a 5. High signal means it's likely to be a 5. You can adjust your threshold, and that will change the output. So you'll see here, here's precision and recall, and here's the threshold. You can make it so that it'll, and even a small amount of signal, it'll call it a 5, and then it will always correctly label the 5s, but it will start labeling some of the non-5s equal to 5s. Or you can make it very high threshold, where it will only say it's a 5 if it's very, very sure it's a 5. And then you'll have a very small chance that a non-5 is called a 5, but a very high chance that a 5 is called a non-5, and so on. So you have this adjustment, and you can play with these things and see it. And then you can try ways of making a 10-way classifier, which you do by assembling a group of two-way classifiers. You can make a one versus the rest, 0 or not 0, 1 or not 1, or you can make all the pairs, of which there are 45, 0 versus 1, 0 versus 2, 0 versus 3. You can make a variety of classifiers using those, and then you'll get a confusion matrix like this. The diagonal is the correct categorizations, and you can see the errors are not uniform at all. Like there is a very small chance that something that is really a 9 is considered an 8, but a high chance that it's considered to be a 7, and so on. So you can represent these things and consider the accuracy that way. So that's another good thing to play with. And then you can play with support vector machines, which I talked about in the introduction a bit. These are the things that use a straight line. So you're trying to tell the reds from the blues. Either one of these lines would do, but the one you choose is the one that has the widest margin between them. Now, in a perfect case, the dots are completely separate, so you can have this kind of diagram. In a realistic case, you allow some errors, so you allow the greens to interpenetrate the blues a little and use more than just one point. But anyway, you can easily calculate this, take some random data to work with, and then you can practice classifying it. So here's a good classification of scale X and Y similar. It draws this line, separates the red from the blue. So that's a support vector machine working in a simple case. But now you can see one of the many dirty tricks. Suppose, notice here my X goes from -3 to 3 and my Y goes from -4 to 4, so it's pretty much the same. Suppose I rescale the Y so it goes by hundreds instead. which is something you get in realistic data. It'll all be measured in different units like pounds and feet and inches and stuff. So now if you train the model, it's going to have this support vector machine because it works by the mean squared error. So you have told it that vertical errors are 100 times more important than horizontal errors. So it is absolutely necessary to get very, very close to these vertical points, and horizontal errors don't hardly matter. This is going to be a problem that keeps coming up. So in addition to all the other adjustments to the data, you typically have to scale all the data so it goes from 0 to 1 on all the parameters. Or if it doesn't, you have to understand why you would choose a different scale and that will have an effect on your cost function. So it's another bit of an issue. All right, and the last, and if you can make overlapping data with a higher degree, and then you can try fitting it. And now we hit another issue of regularization. I mentioned this before. You don't want to overfit. You don't want to fit the noise. You want to fit the trend. And so you do that by not minimizing the loss, but by minimizing loss plus a regularization parameter, which causes it to make more smooth curves. And here it's this parameter called C. And since you don't know what value to use, you just try various values of regularization. So here, the regularization parameter has dominated everything. It's categorized the whole window as blue. So this is terrible. But here, at 0.1, you get a pretty good fit. So you just try various values of regularization until you get what looks to a human eye like a pretty good fit. And that's why I say it's not true at all that the intelligence is coming from the machine. A whole lot of intelligence must be inserted by the human operator. All right. And so if you make a curved data set and then try to fit it with this, then what you can do is you can use polynomial features. Remember I said you can't fit a curve like this with a straight line, but you can if you add more parameters, x1 squared, x1 cubed, x2 squared, x2 cubed, then a higher order polynomial is now a straight line in that higher dimensional space. And so you can add polynomial features, and now you can get a decision boundary like that, which is, from a viewpoint of the model, that's still a straight line. It's still a support vector machine. It's just the projection down to 2 dimensions makes it look curved. And so you can try fitting it with different models of regularization and so on. And here's a 10th degree polynomial. We'll fit it in more detail, but you can sort of see it's overfitting. Here's the one that was sort of realistic. This is a second degree polynomial, I think, but this is a 10th degree. Now it's doing weird things like this, which are probably not really reflective of the underlying population. It's more of that overfitting we've talked about. And the decision of which degree to take and how much regularization to put in is again something a human has to feed in. The AI does not have enough intelligence to do that. So, that's why these things are not going to replace humans. They're just going to be tools in the hands of humans that will have to carefully apply them and apply the common sense that's missing to decide which part of the AI is useful to me, which part of it is actually not helping me. So that's what I wanted to show you. We stop this recording.